Welcome to the fourth session of Fundamentals of Additive Manufacturing Technology. So today we'll be discussing on stereolithography apparatus, subsystems of stereolithography apparatus, and few numericals. So we'll start with the questions. Okay, before starting, I just want to summarize a little bit on stereolithography process. SLA. This is the widely used additive manufacturing process where we can complete the process in a faster. It's the fastest additive manufacturing process. This is the major advantage is that it is the fastest additive manufacturing process. And major disadvantages, it needs a lot of setup, a big resin tank inside which the specimen or the 3D printed part will be processed. Huge setup required. So primarily these are the major disadvantage and disadvantage of process. So first question is, during photopolymerization, what occurs when the reactive monomers in the resin are exposed to UV light? Do they undergo sublimation, release oxygen gas, bond together to form a solid polymer network, convert to a liquid state? Now, first we will, first if we term the word sublimation, it refers directly when it changes from solid to gas without passing through the liquid phase. Now, this is not a characteristic of photopolymerization. Here, it involves the transition of liquid or resin to a solid state. As we have seen in our lectures, that the 3D printed product is made beneath suppose this is a resin tank, and the product is made inside this resin tank. And after this, in this resin bath, the product is made. After the product is made, the product, the specimen or printed part, it comes above the resin tank. So here the sublimation process does not occur. Here the transition of a liquid or resin to a solid state occurs. Now next is, do they release oxygen gas? The release of oxygen gas is also not a common feature of photopolymerization. Here the primary reaction involves monomers in the resin bonding together to create a solid material rather than releasing oxygen gas. And do they bond together to form a solid polymer network? This is the correct option. During photopolymerization, the reactive monomers in the resin are exposed to UV light. These reactive monomers are exposed to UV light, which triggers a polymerization reaction. This creates a polymerization reaction, and through which the name photopolymerization comes. Now the UV light provides the energy necessary to initiate the reaction, causing the monomers to link together and form a three-dimensional network structure. This solid network is what gives the resin its shape and stability. And the third option, do they convert to a liquid state? Now, as already mentioned, photopolymerization involves the liquid resin transitioning into a solid state, not the other way around. The UV light causes the monomers to react and form crosslinks, resulting in a solidified material rather than conversion to the liquid state. So briefly, if we summarize here, what happens is liquid resin transitions into a solid state, and the UV light, and here UV light, resin is exposed to UV light. This creates a polymerization reaction. Now, in this reaction, what happens is UV light provides the energy necessary to initiate the reaction, causing the monomers, suppose which are, you can say, monomers, to link together and form a three-dimensional network. Three-dimensional network. So this was a brief understanding about the polymerization reaction. So now the next question. Now, which of the following is an advantage of using SLA in additive manufacturing? Low initial setup cost, fast printing speed compared to other methods, wide range of available colors for printing, compatibility with various metal materials. Um, if anyone is aware of the answers, can you please type in the chat box? So low initial setup cost. So why this is not correct for SLA or stereolithography method? Now, SLA is widely known for producing high quality parts, producing high quality parts with fine detail. But it typically involves relatively higher initial setup costs compared to other additive manufacturing methods. This is due to the need for a specialized equipment, resin material, and precise calibration. So it is known for producing high quality parts with fine details, but it typically involves high, but it involves very high setup costs, very high setup costs. What is this? What is this? It is involves a specialized equipment, that is a resin tank. In that your resin will be filled and very precise calibration. And what happens is if this is your initial print bed, up, upon this the resin will be filled and the laser will be falling. There will be laser marks. Uh, this will make, this is the UV light which causes the monomers to react and helps in the transitioning of the liquid resin into a solid state. Precise calibration. Now, SLA can provide excellent results, but it is costly and expensive as compared to some other printing methods. Now, fast printing speed compared to other methods. Yes, this is the correct answer. In SLA, we can also go to a range of 10 meter per second. In some cases, um, and it especially when it comes to producing intricate and detailed parts. So for parts with having complex structures, SLA is the perfect option. But again, it is expensive as compared to some other additive manufacturing method. Now This printing process in SLA involves using a laser to selectively cure liquid resin layer by layer, resulting in faster overall printing times for certain applications. Now, wide range of available colors for printing. While SLA can produce parts with a variety of resin colors, this is not unique. A unique advantage of SLA. This can be achieved in various other printing methods also. So this option is ruled out. And next is compatibility with various metal materials. SLA primarily involves the use of liquid resin, not metal materials. It's not inherently compatible with metal materials. Methods like selective laser melting or direct metal laser sintering are most commonly used for additive manufacturing with metal materials. So option B is the correct. Next question. Now, which is the most typical post-processing step required after SLA printing? Now, after completing the SLA printing process, the resulting object will require post-processing. Now, since SLA method requires a lot of support structures, it is printed inside a resin bath, and very fine and intricate complex structures can be prepared, but this requires a lot of post-processing, as there will be a lot of support structures, and removing these support structures is a very difficult task, as we will be using knife or scissors mostly in this SLA method. Now, so from this, after completing the SLA printing process, the resulting object may require post-processing to achieve the desired final appearance, functionality, and surface finish. Now, the first option is sanding the object to remove layer lines. Now, most common this is the most common post-processing step. Correct option is sanding the object to remove layer lines. Most common post-processing step for SLA printed objects. Now, printers build objects layer by layer, and these layers can sometimes be very visible as fine lines on the surface. So, sanding the object gently helps to smooth out these layer lines, creating a more polished and uniform finish. Refilling the resin vat. This step is not typically considered a post-processing step. Refilling the resin vat is part of the pre-printing setup process. Once the printing is complete, the object is removed from the printer and post-processing steps are performed to enhance the final quality. Heating the object to improve strength. Some post-processing techniques generally require heating in some techniques to improve the material strength and stability. However, post curing is done using UV or but however, this is not a typical post processing step. Post curing is done using UV or heat to further cure the printed object to increase its mechanical properties. Now, and applying a layer of liquid metal. Applying a layer of liquid metal is also not a post processing step for SLA printed objects. It is relevant in some other techniques like direct metal laser uh, uh, laser sintering in DMLS or similar techniques. Okay. Next question. This question is about the dead zone in the photopolymerization process in SLA method. Now, what is a dead zone? What is the significance of dead zone? So this refers, so it is the area where oxygen inhibits photopolymerization due to limited UV exposure. Now, where is the dead zone? This dead zone is the area just above the resin surface in the vat where the oxygen from the air prevents the polymerization. Area just above the resin surface in the vat where the oxygen from the air prevents photopolymerization. Now, to be again clear, what is photopolymerization? Process of curing liquid resin into a solid state using UV light. Now, dead zone is the area where oxygen inhibits this process by interfering with the chemical reaction that UV light triggers. Now, dead zone is very significant because it impacts the resolution and quality of the printed object. Suppose the thickness of the dead zone limits the minimum achievable layer thickness in SLA printing. Now, to counter the effects of the dead zone, printers often use mechanisms to separate the printed object from the liquid resin surface, such as using a transparent barrier or a flexible film, often called a peel mechanism, that lifts the cured layer away from the liquid resin after each layer is printed. Now, this separation further reduces the exposure of the uncured resin to oxygen and allows for more accurate and detailed prints. The option D is the correct. Now, we'll discuss why we are ruling the other options. First option is it refers to the area where the UV light is most intense. Now, this is wrong, as the dead zone does not refer to the region of highest UV light intensity. Next is the dead zone is not related to the presence or absence of liquid resin in the vat. And the next is uh, it refers to the maximum curing depth. It has also no relation with the curing depth. Uh, the dead zone has no relation with the curing depth. Okay. The next question. Which parameter affects the depth of cure and accuracy of SLA 3D prints? Okay, so SLA method, stereolithography, is an additive manufacturing technique that uses UV light to selectively cure layers of liquid resin, building up a 3D object layer by layer. Now, the depth of cure and accuracy of SLA 3D prints are influenced by various factors. Now, first is layer height. What happens is layer height is it refers to the thickness of each individual layer in the print. Individual layer in the 3D print. Now, layer height can affect the surface finish of the print. However, it does not directly influence the depth or cure of the accuracy of the print. Uh, it uh, it refers uh, while this layer height can affect the surface of the finish of the print. It does not directly influence the depth or cure of the accuracy of the print. So these factors are more influenced by the resin's curing properties. Now printing speed, what happens in printing speed is printing speed might impact the quality indirectly by giving the resin more or less time to cure, but it is not a direct parameter which affects the depth of cure and accuracy. Now, resin color is color itself is not a primary factor affecting the depth is very clear. Now, photo initiator concentration is the correct option. Now, we'll understand what happens in photo initiator concentration. Now, photo initiators, these are compounds that initiate the curing process when exposed to UV light. Now, the concentration of photoinitiators in the resin directly affects how completely and quickly the resin cures. Concentration of the photoinitiators in the resin directly affects how quickly and completely the resin cures. Now, higher concentrations can lead to a deeper curing within the liquid resin, resulting in stronger and more accurate prints. Inadequate photoinitiator concentration might cause incomplete curing, leading to weaker and less precise prints. Now, thus, proper control of the photoinitiator concentration is crucial in SLA printing to ensure accurate and well-cured 3D prints with consistent depth of cure. So, the correct option is photoinitiator concentration. So next we are moving to numerical questions. Now this is the question related simple question where we have been given the light intensity and the time, and we have to calculate the energy which is delivered during post curing. Let's solve it. Now total energy is equal to UV intensity into time. This is the basic thing. So the UV intensity here is 200 megawatt per centimeter square and time is 10 minutes. Now we'll convert it. Okay, so in time, sorry, there was some lag. Okay, so total energy, it is in question we have been asked in joule. So we'll calculate in joule. Okay, so here 200, if you convert it, it will be 200 into 10 into 60. This will entirely become 12000 megajoule. This will become 1200 joule. The correct option is 1200 joule. Okay. So the next question is, recording stopped, so I'm restarting it. So the next question is, in a SLA, specific SLA requires in a SLA machine, the laser has a Gaussian power intensity distribution with a maximum power of 50 megawatt, and the beam diameter is given 120 microns. Now calculate the power at the edge of the beam where the diameter is 240 microns. Now, first we will describe the power intensity of a Gaussian beam. My recording stopped, so I'll restart it. So the question is, here we have been given a Gaussian power intensity distribution with a maximum power of 50 megawatt and a beam diameter of 120 micron. Calculate the power at the edge of the beam where the diameter is 240 micron. So here I is given, the formula is IR is equal to I naught exponential of minus 2, ignore this part, I by 2 R square by W square. Now your I naught is the power intensity at a radial distance R from the center of the beam. IR is the radial distance power intensity radial distance R from the center of the beam. I naught is the maximum power intensity at the center of the beam. W is the beam radius. Now I naught is given 50 megawatt. Now this formula is for the power intensity of a Gaussian beam. I'll also write what stands each of power intensity at a radial distance R from the center of the beam maximum power intensity at the center of the beam. W is the beam radius. So according to this formula, IR is equal to 50 megawatt exponent into 2 into 2R. R is 100 by 120 square. Now W is given 120 microns and diameter is 240. I think I did a mistake. It is okay. Sorry, both are 120. That is not 100. It is 120. Diameter is 240. The radius is 120, and beam diameter is given 120 microns. Now, after putting all this, we will get approximately 6.766 megawatt, and this is the correct option is option A. Okay. So next question is, in a SLA machine, a certain liquid resin requires a minimum energy density of Gaussian power distribution. Energy density is 20 mJ per millimeter square to achieve a curing depth of 100 microns. If the laser used has a power of 50 megawatt and a Gaussian power intensity distribution with a beam diameter of 150 microns, will the curing depth be achieved with a single laser pass over the resin surface? Now we'll understand this question. So it is being asked whether we will achieve the curing depth with a single laser pass over the resin surface. Assume the curing efficiency is 100%. So to determine if the curing depth will be achieved with a single laser pass, we need to calculate the energy density delivered by the laser to the resin to determine if the curing depth will be achieved with a single laser pass. We need to calculate the energy density delivered by the laser to the resin. Now, okay, the energy density formula is power by beam area into 1000. Okay, energy density is equal to power by beam area into 1000. Now here we are calculating in terms of joule per millimeter square. Now beam area will be, the beam area is pi d square by 4, normal the cross section of a pi into beam dia. Now your beam dia is given 150 microns. This will be 150 square by 4. This will be approximately 17671.88 square microns. Okay. Now we are asked whether we can achieve the single laser pass over the resin surface. Now the energy density we will calculate. Now we have calculated the beam area. We'll put it in this formula and get the energy density. Now the energy density will be from here. This is 50 megawatt by 17671.88 into 1000. Now if you calculate this, you will get, let me calculate it. I'm using the calculator for this. Okay, this comes around 2.83 megajoule by mm square. Now this value the calculated energy density is less than the required minimum energy density. The minimum energy density is 20 megajoule given, but this is less than the minimum energy density of 20 megajoule per millimeter square. So since this is less than the required minimum energy density, so the curing depth of 100 microns will not be achieved with a single laser pass. So if it had been more than the minimum energy density, then we could have achieve the curing with depth in a single laser pass. But since this is less than the minimum energy density, so we cannot achieve with a single laser pass. Any doubt? Is everyone clear with this question? So the correct option is option B. The curing depth of 100 microns will not be achieved with a single laser pass. Okay, so if there are no doubts, we'll move on to the next question. So, okay, which of the following materials about SLA is true? Okay, we have discussed maximum options from this. So, the correct option is it can produce highly detailed and intricate objects. This is the correct option. This is wrong, as resins are also used as an SLA materials. SLA materials limited single occurrence is also wrong, and this is biodegradable is also wrong. Okay. Now the next question. In a SLA 3D printer, the galvanometer scanning system exhibits a distortion of 0.5%. If the desired scanning angle is 120 degree, what is the corrected scanning angle to compensate for the distortion? So, for as we have studied that there are various subsystems in SLA method. One is laser, galvanometer, recoating. Uh, so, so there in galvanometers we have scanning systems. If you are aware of that, I'll just share. My recording is stopped. Okay. So, recoating. Now, recoating is in SLA method we have various subsystems. Out of which one is recoating. Why I am talking about recoating is we have a difference with recoating with regard to in SLA process we have two different methods like 3D system SLA. One is the conventional method, another is 3D system SLA, which is the Zephyr technology. Now, the recoating we have two types of top feeding and bottom feeding. Now, the SLA 3D system SLA considers the top feeding technology. In these both SLA methods, we have only one difference in the various subsystem, that is the 3D system Zephyr technology. This is top feeding technology. Now, why I am saying all this is because recoating is the process of establishing a new layer of fresh resin over previously cured layer. So successful recoating is one that is capable of establishing a fresh layer of liquid resin of thickness exactly equal to the desired thickness within a reasonably short time. So there are various stages. One is leveling, stages of recoating. One is leveling, deep dipping, elevating, sweeping, sorry, excuse me. Next is obtaining build position, now the differences, this is top, this is bottom, and this is the very important point in SLA method. So top feeding and deep dipping. So deep dipping is followed by 3D system SLA, and the top feeding is followed by 3D systems SLA. Rest all scanning system, which is galvanometer, shape of UV light, which is laser beam, shape of liquid, which is liquid vat, build direction, which is in the direction, all are same for both the methods. Now there are also various other SLA methods like micro stereolithography, object polyjet, autostate EDAT. These also have again various other specifications. And in recoating system, we again have deep dipping, top feeding, and bottom feeding. Next in pre-processing, build process, post-processing, advantages, limitations, we already discussed little bit. Um, and regarding the curing process, uh, how like there are like it first goes the laser first goes inside, then the curing of an intermediate laser layer happens by a UV laser, then deep dipping happens, then wiping of the extra material using a doctor blades happen, then the raising level scanning. This is the process which is followed. And the recoating system is used to spread the new liquid on rebuild geometry. Uh, next in this photopolymerization based liquid name, the laser beam topic is there, which is which is also one of the subsystem where we further study about the various laser principles and the Gaussian power intensity distribution of a laser beam, which we calculated and solved a question, and um, further discussion had been done on the laser principle on for the Gaussian beam, real beam, and some numericals on that, and then laser curing method, how much time in a single bead laser can achieve the energy per unit square, so all those things. So further after the next topic, exposure time also we discussed, in like in how much time a single laser beam can pass through a single laser beam. So next all the question which is from 13 to 20, this will solve completely detailed after the assignment is submitted, and any other doubts you can ask me now. Is everyone clear specifically in this question where we found out the curing, whether the curing depth can be achieved with a single laser pass over the radiant surface?